Lecture 26 today, more stuff with series. I never really got a chance to focus on what absolute convergence was last time, so I'm going to start with that, versus what's called non-absolute or sometimes conditional convergence. Then we'll get back into power series, and in particular in Lecture A, I want to focus how geometric series can be thought of as power series if you think of one of the quantities involved as being a variable. Then Lecture B, power series in general, and getting into what are called Taylor polynomials and Taylor series. Reminder that next Monday there's an extra credit opportunity, 7 o'clock in CC 313. Probably be about an hour long. You can get 5 points of extra credit for your homework. 3 alums of the math and computer science major will be there to answer questions about what life is like after school, how do they get a job, what kind of job do they do, how does their Bethel education affect their job, what did they get out of their education, and it will be beneficial to not just math and CS majors, but any majors. I still have to think of a short alternative assignment. If you can't make it, that alternative assignment would be due the next Wednesday, and you'd hand it in separately from the regular assignment. All right, what is absolute convergence versus non-absolute convergence? That's what we'll focus on first. A series, k goes from 1 to infinity of ak, converges absolutely if another series, a series whose terms are the absolute values of the AK, converges. These AKs might be negative. If you make them all positive, and consider that corresponding series, if this converges, I didn't state this right. Series converges absolutely. Forgot the most important words there. If this series converges, which actually begs a question, there's a theorem that really should be proved before you define this. And that theorem is that if such a series like this converges, then the original series will converge. That's a theorem. This is a definition. I really should have given the theorem first. Absolutely convergent series are convergent, is the point that I'm trying to make. The theorem says if a series of absolute values of AKs converges, then so too does the series without the absolute value signs. So the theorem should really be proved first. And then once you have the theorem, then this definition makes more sense. A series converges absolutely if this series converges. If you don't have the theorem, you might wonder, does that mean this series converges? Because I'm only, in this definition, I'm only assuming that converges. This theorem guarantees that this series will converge. If, in addition, this one converges, then we say this series converges absolutely. A little confusing. Let's consider an example. Let's consider this example. The content we're doing today is pretty much very similar content, at least right now, to what I taught in my senior level class called Real Analysis this morning. And we even considered this example this morning. There's a series that's alternating. This one's alternating in sign. This is a 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared, etc. That's an alternating series. Does it converge? The alternating series test implies it does converge. Remember the alternating series test? We talked about that on Wednesday. These are the terms the expression 1 over k squared without the negative 1 to the k plus 1 power is a sequence that decreases to 0 as k goes to infinity. And this series, where you not only have this, but you also have negative 1 to the k plus 1 so that it alternates in sign, does satisfy the conditions of the alternating series test then, because again, this is a sequence that decreases to 0 and this alternates in sign, plus minus plus minus. Therefore, by the alternating series test, this series does converge. Track with me there? Should I say it again quick? These are the terms of the series. Get rid of that negative 1 to the k plus 1, I get this sequence. That's a sequence that's positive values that decreases to 0. Because this also alternates in sign, plus minus plus minus, the alternating series test implies that this series does converge. Does it converge? Absolutely. Consider the corresponding series whose terms are the absolute values of the terms of this series. This can be simplified. I can get rid of that negative 1 because I'm taking the absolute value. I can rewrite this series without absolute value signs as just the sum of 1 over k squared. But that's a p series with p equal to 2. 2 is bigger than 1. It, what? Converges. Therefore, this series does converge absolutely. This series is an absolutely convergent series. Are there examples of non-absolutely convergent series? What would that mean? This converges absolutely. If that converges, I suppose it would make sense to say a series converges not absolutely if it does converge, but this does not. And that, in fact, is correct. That's what you should say non-absolutely convergent means. A series converges non-absolutely. I'll go ahead and make a new definition. This is a new definition. Converges non-absolutely if it converges but this one diverges. This is a new definition. Just modify the old definition. And yes, in some books, including our book actually, you will see this called conditional convergence. They will say a series converges conditionally if it converges, but that diverges. That's actually the more common way to describe it, is conditional convergence. However, I like using non-absolute convergence. It's sort of to say it's the opposite in the sense of absolute convergence in the situation where your series does converge. What's an example of a non-absolutely convergent series? The alternating harmonic series is one. If I get rid of this 2 here, I make it the alternating harmonic series. That does satisfy the hypotheses of the alternating series test. You're getting rid of the negative 1 to the k plus 1, considering this sequence right there, 1 over k. That's a sequence of positive terms that decreases to 0. Therefore, the alternating series test says this alternating series does converge. The alternating harmonic series does converge. But the harmonic series diverges. The series of absolute values of these things is the harmonic series, and that diverges. Therefore, this series converges non-absolutely. You can also say it converges conditionally. Absolutely convergent series are, in a sense, better than non-absolutely convergent series. They're more robust. Saying this in my morning class just this morning. You can swap around the terms of an absolutely convergent series, and you're still going to get the same sum, even though the sequence of partial sums will actually be different. Non-absolutely convergent series, like the alternating harmonic series, are kind of fragile. You can sort of break them. What do I mean by that? I mean, you can rearrange the terms of a non-absolutely convergent series like this and get a different sum. In fact, you can even make it add to whatever you want, or make it even diverge if you rearrange the terms appropriately. I won't explain why, but...
Oh, I was just going to ask if we could see an example of rearranging the terms to make it add up differently.
Maybe next time. I want to get to some other stuff.
Okay. Okay.
If you could remind me in an email over the weekend, I'll come back and we will look at that next Monday.
Okay.
Talk about rearranging to make it add up to something else. It's kind of fragile because of that. You can even make it diverge if you rearrange the terms appropriately. The way they are right now, it does converge. In fact, we saw it to natural log of 2 of this series. But it's a fragile kind of convergence. That's what non-absolute convergent series, in my mind, kind of means. Ideally, we look for absolute convergence because that's more robust. Including, for power series, on their interval of convergence. In fact, actually, for your general power series, I'm not going to write it down right now, but in lecture B we will. It's going to have, in general, an interval of convergence, which typically will be an interval centered at A, with a certain radius, distance between the center and either endpoint. Inside the open interval, where you do not consider the endpoints, the series converges absolutely, but you can get fragile convergence, non-absolute convergence at endpoints, or it might diverge at the endpoints. I said part of lecture A, another part of lecture A that we're going to do here now is consider the fact that geometric series can be used to generate power series. Here's an example of a geometric series that is also a power series. Doesn't look geometric when you just look at it necessarily, unless you look at it in the right way. There is a common ratio. There is a quantity that I can take and multiply each term by to get the next term. Or that I can take any given term by, except the first one, and divide by the preceding term to get that common ratio. The common ratio does involve x. The common ratio is x minus 3 over 4. In each case, multiply by x minus 3 over 4. This x was supposed to be at times. Probably would be better to put a dot. Keep multiplying by x minus 3 over 4 to get the next term. It is a geometric series. The first term is 5. The common ratio is x minus 3 over 4. You could call this R. We didn't typically call it R before, but we can call it R now. R standing for common ratio. This is going to converge to A over 1 minus R if the absolute value of R is less than 1. This thing here is the A. A represents the first term. So what will that equal here? A is 5. R is x minus 3 over 4. That's what it converges to. This can be simplified a bit. We can multiply the top and the bottom by 4 to get rid of the 4 there. And get 20 over 4 minus, careful with parentheses, x minus 3. That's the same as 20 over 7 minus x. This works as long as the absolute value of R is less than 1. R is x minus 3 over 4. This is true then if the absolute value of x minus 3 over 4 is less than 1. That's equivalent to saying the absolute value of x minus 3 is less than 4. It's also equivalent to saying x is between -1 and 7, because -1 and 7 are 4 units away from 3. So far I've thought of this completely in terms of geometric series, but once you're done, you realize, hey, that is a power series. It is of the form that we wrote down for power series in general. Some constant, call it C0, plus another constant C1 times x minus a, plus another constant C2 times x minus a quantity squared, plus another constant times C3 times x minus a quantity cubed, etc. A is 3. That's the thing you keep subtracting. C0 is 5. C1 is 5/4. C2 is 5/16. C3 is 5/64. C4 would be what, 5 over 256. It does fit that pattern. It is a power series. And therefore it's got an interval of convergence. And hey, there's the interval of convergence right there. It's an open interval. Centered around 3. It's open. It does not contain its endpoints. It does have a radius of convergence of 4. We don't need to check the endpoints. The endpoints are not part of the interval of convergence here, because we already know this only worked when the absolute value of the common ratio was less than 1. In this case, when this is true. This is the interval of convergence for these geometric series that are also power series. The interval of convergence will not include the endpoints. Could I have calculated that radius of convergence with the ratio test? Sure, I could have. Let's go ahead and do that. So let's use the ratio test to confirm that the radius of convergence is 4. I would suggest every time you use the ratio test, writing down the limit in abstract form first. And again, with these power series, you have to keep the absolute values there. They are essential to keep there. They don't go away like they did with some of the first few examples. Because x could be negative, and in particular x minus 3 could be negative for this example. What's your general AN here? This, for example, is, well, this would be A. You could call that A1, you could call this A2, A3, A4. You could call this A4 if you like. You also could call it A3 if you called this one A0, but we don't typically do that. You could write this term, A4, as 5 over, 2 to the third times x minus 3 to the third Evidently, the pattern is, based on that AN would be 5 over 2 to the n minus 1 times x minus 3 to the n minus 1. So again, it's a little confusing because I could have called this A0 to start with.
Wouldn't it be 4 to the third?
Thank you. I don't know why I thought 2 there. I'm calling that A4 because I'm thinking of this as being A0, A1, A2, A3. Oh, I wasn't thinking of it that way. I was thinking of this being A1. A1, A2, A3, A4. A little confusing though, with power series we start with C0. So I could have called this A0 or A1, A2, A3, and then the formula would be a little different. There would be an nth power there and there instead of an n minus first power. It doesn't really matter. Okay? The ratio, the limit of the ratio test is going to be the same either way. If I replace these n's with n plus 1s, then I actually get n's because of the minus 1. And if I don't replace the n with n plus 1, then I get what you see up there. Again, it really doesn't matter. You could also have an n plus 1 there and an n plus 1 there, along with an n there and an n there. It's going to simplify to the same thing either way. You get cancellation. What cancels? The 5s cancel. All the x minus 3s cancel except for one of them up top. All the 4s cancel except for one of them. You're going to get the absolute value of x minus 3 over 4. If you are careful in how you think about simplifying them. The 5s go away, they cancel. That x minus 3 to the n minus 1 completely cancels with this one, except 1 is left over. The 4 to the n minus 1 completely cancels. There's 1 4 left over. It's in the bottom, so it's got to go in the bottom there. And I can get rid of the absolute values around that. We know from the ratio test that the series will converge if and only if this limit is less than 1, when the limit exists. This is for convergence. Actually, what the ratio test implies is if that is less than 1, then it will converge the series. This is equivalent to, since this limit doesn't depend on n, in fact, I should really do this. This limit does equal the absolute value of x minus 3 over 4 without a limit sign anymore, because there's no n there. It's a constant in terms of n. We want that to be less than 1 for convergence. That's equivalent to saying the absolute value of x minus 3 is less than 4, the exact same thing I wrote there. So the ratio test confirmed the same radius of convergence. But because it was also geometric, this was a strict inequality, so this is strict. Definitely we do not include the endpoints as part of the interval of convergence for this example.
Is that because it's geometric? Or is it
Yep, because of geometric, because of that condition right there. We saw on Wednesday that there are examples where you do include the endpoints, and maybe one endpoint but not the other. That was the example we considered on Wednesday. The answer was 20 over 7 minus x. That's a function of x. I could think of this thing as being a function. 20 over 7 minus x. Again, let me see what happens when I graph these things. Plot. I'm going to plot two functions here. 20 over 7 minus x. And the infinite sum, this infinite sum right here, is a power series. I guess I will start the index at 0. Maybe I should have done the index at 0 with this one too. I should have called this A3. And I should have had n there and there. Maybe that would have been less confusing. Let's start the index at 0. What am I adding up? I'm adding up fractions of the form 5 times x minus 3 to the k power over 4 to the k. And I'm starting at 0. The 0th powers are going to be 1. I'm just going to get a 5. When k is 1, I do get this. When k is 2, I do get this. that is the infinite series, it can be thought of as a function of x. Let's graph it over the interval of convergence, -1 to 7. What am I thinking I'm going to see here? Well, if one of them is red and one's blue, does that mean if they're really the same graph that we get purple? One purple graph? I guess so. It's kind of purplish. A little hard to tell. Looks halfway between purple and blue. Yeah, it's actually both graphs. They are the same graph. If you don't believe me, I could, add one to one of them and see that you get two separate graphs that are vertical translations of each other. One red, one blue. They are the exact same graph. Maybe 0.1 will make the point even more clear. You can see the slight difference between red and blue there. Get rid of the 0.1. These are the exact same function. And why did it not graph?
Plus sign.
There we go. They are the exact same function. What if we made our interval bigger, though? What would happen? Oh, sum does not converge. Error. Something goes wrong if we use a bigger interval. The red graph is actually still there. This is actually a vertical asymptote for the red graph. It's not part of the red graph. Let me go further to the right here than 8. Let's go, I don't know, 12 maybe. Sum does not converge. The summation is having a problem, but 20 over 7 minus x is still there. Again, this is not part of the graph. It's a vertical asymptote. You can get rid of vertical asymptotes, by the way. You can do exclusions, arrow. I think I got to do x double equals 7, maybe inside the curly braces here. Yeah, I got rid of the vertical asymptote. I'm excluding Mathematica from plotting this at x equals 7. Interesting, you see the blue graph of the summation only between -1 and 7. 7 is a vertical asymptote. They're the same just on that interval. Not at the endpoints, not at 7, and actually not at -1, though you can't tell that from looking at this. And you look at it, you might wonder, well, why couldn't it work at -1? I mean, they're equal up to -1. Why couldn't it work at -1? You might wonder. Actually, let's do something else now. To avoid this sum does not converge thing, let me do finite sums instead of infinite sums. Make that an n. And let's watch what happens if we manipulate this, animate it, as n increases here. Say from 0 to 10 in step units of 1 step at a time. Shouldn't get any errors this time because it's a finite sum. Don't have to worry about an interval of convergence for a finite sum.
I just have a question.
Mm-hmm.
So, on the sum, you put k goes from 0 to n,
Mm-hmm.
but I don't see any n in the function. So what does that n represent?
I'll tell you in a second here. Let me just type this in here like this.
Oh, never mind. I see the n at the end of the equation now.
Yeah, it's going to be the animation parameter. It's going to be the thing that keeps increasing in the animation. I have to add the extra comma 1 to make it increase by 1 unit each time instead of continuous increasing. What do we have here? When n is 0, the red graph is 20 over 7 minus x. The blue graph is, when n is 0, I guess it's just 5. Yeah, 5. 5. What happens when n increases to 1? The red graph should stay the same. The blue graph is going to be the sum k goes from 0 to 1 of that expression. It's going to be the graph of 5 plus 5 fourths times x minus 3. It should be a straight line with a slope of 5 fourths going through the point 3, 5. Straight line with a slope of 5 fourths going through the point 3, 5 right there. Is that the slope 5 fourths? If the slope is 5 fourths, if I let x decrease from 3 down to 0, y should decrease by 5 fourths 3 times by 15 fourths. 3.75 from 5 down to 1.25. That is 1.25 there. 2. 1's halfway between, it's 1.25 for the y-intercept. This blue graph is aligned with a slope of 5 fourths. Y-intercept at 1.25. It goes to the point 3,5 is the most important thing about it besides the slope. Plug in x equals 3. You get 0 there. 0 plus 5 is 5. It's got to go to the point 3,5. When n is 2, I guess I'm going to get the graph of this thing, a quadratic. It's going to be a parabola. Still going to the point 3,5. Because when x is 3, this is 0, and that's 0, I get 5. The slope is still going to be 5 fourths at x equals 3. We can also figure out the second derivative at x equals 3. That would be 5/8, though it would be something you can't really visually see. Hard to visually estimate a second derivative. It's going to be a parabola. There's the parabola. It does go to the point 3,5. It is a parabola, though we're not seeing it over here real well. It's centered at, this is 3,5. Well, okay, the min is not occurring at x equals 3. It's occurring somewhere between 1 and 2, it looks like. If I centered this domain here to be, let's just say negative, centered at 1, it already goes up to 12, which is 11 units above 1. If I made this negative 10, it would go 11 units below 1 as well. Then the graph of that parabola, oops, got to do this too. Then the graph of that parabola is going to be basically symmetric in the picture. That's what I was trying to get. It is a parabola. I was trying to emphasize it is a parabola. Actually, just because something looks like a parabola doesn't mean it is a parabola. You can have lots of graphs that are shaped like this that are not parabolas. Parabolas are technical things. It's a very special kind of curve. So it goes to the point 3,5. Now watch as I play and keep increasing it. Watch it here. Cool, it's like a dog wagging its tail. It converges to the red graph pretty rapidly over here in the range of values, say, between 0 and 6 or so. Over here, as x gets close to -1, the left endpoint of the interval of convergence for the infinite series, convergence is slower. And I guess the fact that it's so slow is sort of an intuitive reason why you can maybe see why it doesn't get past -1 in the infinite sum. When x is -1 or smaller, the infinite sum does not converge. But you certainly can't prove it from the picture, but the picture makes it plausible. Let's take our break.